Hello everyone and welcome to lecture 4 about integers, in which we will explore the famous Euclidean algorithm and we will see why and how it works. We've seen in the previous lecture that prime numbers are the building blocks of positive integers because any of them is a product of primes. However, as we shall see in future lectures, it is not very easy to decide whether a given natural number is prime, nor to find the prime factorization of a given number. Instead of studying the divisors of a single number, it is better to study the common divisors of two numbers a and b. In Book 7 of the Elements, Euclid described a very efficient way to find the GCD, which, let me remind you, means the greatest common divisor of two numbers a and b. This famous and important algorithm threw light on prime numbers and prime factorizations, as we shall see together. In this first part, we describe the GCD by subtraction algorithm. Let a and b be natural numbers with a common divisor d. We can then write a as a prime times d and b as b prime times d for some natural numbers a prime and b prime. It follows from this that d must divide a minus b as well, and this is a trivial fact because this is equal to a prime d minus b prime d, which is equal to d times a prime minus b prime. In other terms, a common divisor of a and b is also a divisor of a minus b. Euclid, our eminent ancestor, used this fact to compute the GCD of two natural numbers a and b by repeatedly subtracting the smaller number from the larger. And this works because from here we deduce that the GCD of a and b, which means the greatest common divisor of a and b, is actually equal to the GCD of b and a minus b. I hope that this is obvious to you because the divisors of a and b are the same divisors of b and a minus b, which means that the greatest among them is the same. And this is actually because if d divides b and divides a minus b, then d must divide b plus a minus b, which means it divides a as well. Do you get that? Let us try this on a simple example. For practical reasons, I will denote GCD of AB by only AB. Now if you take A equals to 42 and B equals to 30, we see that the GCD of 42 and 30 is equal to the GCD to 30 and 42 minus 30, which is equal to the GCD of 30 and 12. Now the GCD of 30 and 12 is equal to the GCD of 12 and 30 minus 12, which is also equal to the GCD of 12 and 18. Moreover, the GCD of 12 and 18 is equal to the GCD of 12 and 18 minus 12, which is equal to the GCD of 6 and 12. Now the GCD of 6 and 12 is equal to the GCD of 6 and 12 minus 6, which is equal to the GCD of 6 and 6. Finally, the GCD of 6 and 6, which means the greatest common divisor between 6 and 6, it is obviously 6 actually, but I'll do this one more time. It is equal to the GCD of 6 minus 6 and 6, which is equal to the GCD of 0 and 6, and we know that the greatest common divisor of 6 and 0 is equal to 6. This means that the GCD of 42 and 30 is equal to 6. Let us try this on a second example. We would like to compute the GCD of A equals 70 and B equals to 42. By the Euclidean algorithm, we know that the GCD of 70 and 42 is actually equal to the GCD of 42 and 70 minus 42, which is equal to the GCD of 42 and 28. Now if you do this again, we know that the GCD of 42 and 28 is equal to the GCD of 28 and 42 minus 28, which is equal to the GCD of 28 and 14. Now the GCD of 28 by subtraction and 14 is equal to the GCD of 14 and 28 minus 14, which is equal to the GCD of 14 and 14. Now if you do this one last time, the GCD of 14 and 14 is equal to the GCD of 14 and 14 minus 14, which is the GCD of 14 and 0, and we know that the greatest common divisor between 14 and 0 is equal to 14, and this means that the GCD of 70 and 42 is equal to 14. We notice that this process always terminates because it produces smaller and smaller natural numbers, which by the principle of infinite descent must halt. Instead of doing repeated subtractions, one can speed up Euclid's form of the GCD algorithm by doing division with remainder, which is, let me remind you, essentially repeated subtractions. The main result that makes things work is that the GCD of AB is equal to the GCD of B and R, where R is the remainder of the division of A by B. Indeed, if you divide a by b, one gets a equals to b times q plus r, where q is a quotient and r is the remainder. And if d is a common divisor of a and b, then d must divide the difference between a and b times q, which is a minus b times q, and this is equal to r. So here we proved if d is a common divisor of a and b, then d must divide r. Conversely, if d divides b and r, then d must divide a, because a is a combination of b and r. This means that common divisors of a and b are the same common divisors of b and r. Thus, they have the same great common divisor. And we will use this repeatedly to compute the GCD of two numbers a and b. Let us see how things work on a concrete example. We get back to our first example to compute the GCD of 42 and 30. To do this, we divide 42 by 30 to get 42 is equal to 30 times 1 plus 12, and this equality here implies that the GCD of 42 and 30 is the same thing as a GCD of 30 and 12. Now we divide 30 by 12 to get 30 is equal to 12 times 2 plus 6, which means that the GCD of 30 and 12 is equal to the GCD of 12 and 6. We do this again and divide 12 by 6, we get 12 is equal to 6 times 2 plus 0, and this means that the GCD of 12 and 6 is equal to the GCD of 6 and 0. And this ends our algorithm because the GCD of 6 and 0 is equal to 6. We obviously see that applying division with remainder speeds up the algorithm. So instead of doing this in 5 steps, we did the computations in 3. Division with remainder actually speeds up drastically subtractions when our numbers are very big, which I hope is obvious to you. Let us now take another example and compute the GCD of a equals to 858 and b to 770. We begin by dividing 858 by 770 to get 858 is equal to 770 times 1 plus 88, and this means that the GCD of 858 and 770 is equal to the GCD of 770 and 88. Now if you divide 770 by 88, we get 770 is equal to 88 times 8 plus 66, which means that the GCD of 770 and 88 is equal to the GCD of 88 and 66. Now by dividing 88 by 66, one gets 88 is equal to 66 times 1 plus 22, which in terms of GCD means that 88 and 66, actually the GCD of them, is equal to the GCD of 66 and 22. Now a last division, 66 is actually equal to 22 times 3 plus 0, which means that the GCD of 66 and 22 is equal to the GCD of 22 and 0, and we know that this is equal to 22. These computations mean that the GCD of 858 and 770 is equal to 22. We see that this only required 4 steps instead of many more with simple subtractions. And I wrote a little computer program with Python to do the comparison, so let us see how this is done. This first function, which I call GCD_div, uses division with remainder to compute the GCD, and GCD sub here means GCD with subtraction. Notice here that the while halts when the last remainder is equal to 0, and that the number I here is going to count the number of steps that I use to compute the GCD. Now if you execute the function GCD_div, which means GCD with remainder, with the numbers GCD of 858, GCD_div, of 858 and 770, we get that the GCD is equal to 22, and the number of steps is equal to 4, which corresponds to what we've done. Now if you try with GCD subtraction, one gets a lot more steps actually, and here as you see we get the GCD which is equal to 22, but 13 steps instead of 4, right? I suggest you write these programs by yourself and check with other numbers that GCD with remainder is a lot faster than GCD with subtractions. It is very important when we design an algorithm to know in how many steps it can be done. The Euclidean algorithm is very efficient, and we will see why in future lectures. We now move on to a very important consequence of this algorithm, which is that we can write the GCD as a linear combination of a and b, namely the GCD of a and b will be equal to a certain integer n times a plus another integer m times b. Examples are way better than a long talk. For instance, to compute the GCD of 42 and 30, we've done the computations 42 is equal to 30 times 1 plus 12. Then we divided 30 by 12 to find that 30 is equal to 12 times 2 plus 6. And finally that 12 is equal to 6 times 2 plus 0. We deduce from this that the GCD is the last remainder not equal to 0, so 6 is a GCD here, and we would like to find integers n and m such that 6 is equal to 42n plus 30m. Indeed, from this equality here, we deduce that 6 is equal to 30 minus 12 times 2. And from this first equality here, we deduce that this is equal to 30 minus 42 minus 30 times 1. This is because 12 is equal to 42 minus 30 times 1, all times 2. If we develop the expression to the right, one gets that this is equal to 30 minus 42 times 2 plus 30 times 2, and this is equal to 30 times 3 plus 42 times minus 2. Hence, m is equal to 3 and n is equal to minus 2. And if you would like to verify this is equal actually to 90 minus 84, which is of course equal to 6. Bingo. Let us try this on a second example, and we know from previous computations that the GCD of 858 and 770 is equal to 22, and we would like to find integers n and m such that 22 is equal to 858 times n plus 770 times m. If we write down the successive divisions, we know that 858 is equal to 770 times 1 plus 88. We also know that 770 is equal to 88 times 8 plus 66. 88 is equal to 66 times 1 plus 22. And finally, 66 is equal to 22 times 3 plus 0. So we're going to work out the Euclidean algorithm backwards. We start from this equation here, from which we deduce that 22 is equal to 88 minus 66 times 1. And now we replace 66 by the equation here, and we get that this is equal to 88 minus 770 minus 88 times 8, all times 1, which is equal to 88 plus 88 times 8 minus 770 times 1, and this is equal to 88 times 9 minus 770 times 1, and now we replace the 88 that's here with the equation that is here to get that this is equal to 858 minus 770 times 1, all times 9 minus 770 times 1. From here we get that 22 is equal to 858 times 9 minus 770 times 10. Or more equivalently, this is equal to 858 times 9 plus 770 times minus 10. Bingo, so n is equal to 9 and m is equal to minus 10. You can check by yourself if this is actually true. And of course, to understand better what I'm doing, you have to do the computations by yourself. Working out the Euclidean algorithm backwards is called the extended Euclidean algorithm. Our aim now is to computer program this with Python, and to do so, one has to write things down more formally. Indeed, we would like to describe the sequence of remainders, which we will call Rn. For practical reasons, we will denote A by R0 and B by R1. Now, the Euclidean algorithm consists of dividing first R0 by R1 to find that R0 is equal to R1 times Q1 plus a new remainder, which we denote R2. Step 2 consists of dividing R1 by R2, and we find that R1 is equal to R2 times Q2 plus a new remainder, which we denote R3. Now, step 3 is mainly the same thing. We divide R2 by R3, and we find that R2 is equal to R3 times Q3 plus a new remainder R4. We do this repeatedly until we get to Rn minus 2 is equal to Rn minus 1 times Qn minus 1 plus Rn, and then we divide Rn minus 1 by Rn to find that Rn minus 1 is equal to Rn times Qn plus 0. We've seen that this means that Rn is the GCD that we're looking for. Let me remind you that we would like to write Rn as a linear combination of R0 and R1, which means of A and B. Moreover, this sequence always goes down to 0, and this is because the decreasing sequence of natural numbers must halt. And this is a beautiful and important consequence of the infinite descent of Fermat. So we would like to write Rn as a certain integer x times R0 plus another integer y times R1, which means x times A plus y times B. In order to do this, we first transform this equation and solve for R2 to find that R2 is equal to R0 minus R1 times Q1. Now we solve the second equation in R3 to find that R3 is equal to R1 minus R2 times Q2. And since I would like only an expression in R0 and R1, I will transform R2 by using this one here to find that R3 is equal to R1 minus R0 minus R1 times Q1 all times Q2. Now if you simplify a little bit further, we find that this is equal to R1 times 1 plus Q1 times Q2 plus R0 times minus Q2. Now all we have to do is to do this again with R4. We transform this equation here as R4 equals to R2 minus R3 times Q3, and then replace R2 by the expression here and replace R3 by the expression which is here, and they are both function of R0 and R1. We do this repeatedly until one gets to Rn as a function of R0 and R1, which means that we will get that Rn is equal to a certain integer x times R0 plus another integer y times R1. This doesn't seem very helpful, but if you go through this again, we notice that each remainder Rk can be expressed as a function of R0 of R1. This is the case of R2 here. It is also the case of R3, which is also a function of R1 and R0. R4 will be the same thing until we get that Rn is a linear combination of R0 and R1. Thus, one can write that for every integer k, that the remainder Rk is equal to a certain integer xk times R0 plus another integer yk times R1. Now all we have to notice that the procedure that gets us from R2 to R3 is the same one that gets us from R3 to R4, etc., which suggests that there must be a recursive relation that gets us from xk to xk plus 1 and from yk to yk plus 1. And to do this, we will investigate how to get from Rk to Rk plus 1, which is equal to xk plus 1 R0 plus yk plus 1 times R1. Let me write things down again properly. We will need further information, which is that Rk minus 1 is equal to xk minus 1 times R0 plus yk minus 1 times R1. We will also need that Rk is equal to xk R0 plus yk R1, and from both of these we would like to derive Rk plus 1, which is equal to xk plus 1 R0 plus yk plus 1 R1. Now when we run the Euclidean algorithm, Rk minus 1, Rk and Rk plus 1 are linked with a relation that Rk minus 1 is equal to Rk times Qk plus the new remainder, which is Rk plus 1. From here we see that Rk plus 1 is equal to Rk minus 1 minus Rk times Qk, and now we replace Rk minus 1 by xk minus 1 R0 plus yk minus 1 R1, and Rk with the relation xk R0 plus yk R1, which gives that we have here minus xk R0 plus yk R1 all times Qk. And if you do further simplifications, one gets that Rk plus 1 is equal to xk minus 1 minus xk Qk all times R0 plus yk minus 1 minus yk Qk all times R1. From this, we get that the sequences xk and yk are defined recursively by the relations xk plus 1 is equal to xk minus 1 minus xk Qk, and it's the same thing for yk, which gives that yk plus 1 is equal to yk minus 1 minus yk Qk. We see here that xk and yk are defined by the same recursive relation, but they will differ by their initial values. Indeed, we know that R0 is equal to x0 times R0 plus y0 times R1, and this means that we should take x0 equals to 1 and y0 equals to 0 to get that R0 is actually equal to R0. Moreover, we have R1 is equal to x1 R0 plus y1 R1, which gives that x1 must be equal to 0 and y1 must be equal to 1. Let us see how things work on a concrete example. First, if I write things down again, we know that the sequence xk is given by x0 equals to 1 and x1 equals to 0, and xk plus 1 is equal to xk minus 1 minus xk times qk. We also have that the sequence yk is defined by y0 is equal to 0 and y1 is equal to 1, and yk plus 1 is equal to yk minus 1 minus yk times qk. Now we know from previous computations that the GCD of 42 and 30 is equal to 6, and we would like to run the extended Euclidean algorithm to find integers n and m such that 6 is equal to 42 times n plus 30 times m. Now we know that for k equals to 0, that qk has no value but xk, which is x0 is equal to 1, and here y0 is equal to 0. Now in order to compute q1, all we have to do is to divide 42 by 30, which gives 42 is equal to 30 times 1 plus 12, which means that q1 is equal to 1. So for k equals 1, we have q1 which is equal to 1, and we have x1 which is equal to 0, and y1 which is equal to 1. And I derive this from the definition of xk and yk. Now for k equals 2, the recursive relations give that x2 must be equal to x0 minus x1 times q1, and this is equal to 1 minus 0 times q1, which is equal to 1. So we know from here that x2 is equal to 1, and y2 is equal to y0 minus y1 times q1, which gives 0 minus 1 times 1, and this is because q1 is equal to 1, and this is equal to minus 1. So we know that y2 is equal to minus 1. Now to compute q2, all we have to do is to run again the Euclidean algorithm to find that 30 is equal to 12 times 2 plus 6, which means that q2 is equal to 2, and we run our sequences again to find that x3 is equal to x1 minus x2 times q2, and this gives 0 minus 1 times 2. This is because x2 is equal to 1 and q2 is equal to 2, and this gives minus 2, which means that here we have minus 2, and in the same fashion one computes y3, which is equal to y1 minus y2 q2, which after computations is equal to 3. And so here we have 3. Our procedure ends here because if we perform one more division, one gets 12 is equal to 6 times 2 plus 0, and we see that our sequence RK halts here. This means that our numbers n and m that we're looking for are minus 2 and 3. And you can check by yourself that 6 is equal to 42 times minus 2 plus 30 times 3. Aha, very nice. And now we're ready to computer program this with Python, and the key ingredient is to know how to computer program a sequence with two initial values. Indeed, I wrote the program here EUC for Euclidean extended, which takes a and b as parameters and returns the GCD of a and b and the coefficients x and y that we're looking for. Here I initialize both of the sequences, and we see here that the while procedures halts when the last remainder is equal to 0. And if we run our algorithm with 42 and 30, one gets 6 as the GCD, minus 2 and 3 for n and m. Aha, very nice. I recommend you do this by yourself and check the algorithm for more integers. What we have done so far is called the Bezel identity theorem, and relations like this one is called the Bezel identity, named after the great French mathematician Etienne Bézout. Our theorem states that if a and b are integers not both 0, and if d is the GCD of a and b, then we can find two integers n and m such that d is equal to a times n plus b times m, which means that d is a linear combination of a and b. This theorem is very useful in the theory of divisibility of integers. Let us see together some of its consequences. We know from the definition of the GCD of a and b that it is the greatest common divisor of a and b, which means that if r divides a and b, then r must be lesser than the GCD of a and b. However, it is not obvious that r divides actually the GCD of a and b. Indeed, to prove this, we know that the GCD of a and b is equal to a times a certain integer m plus b times a certain integer m, and this is the Bezel identity theorem. Now, if r divides a and b, we can write a as a prime times r and b as b prime times r. Thus, the GCD of a and b is equal to a prime times r times n. Here I replaced a by a prime times r plus b prime times r times m. Now it is easy to see that we can actually factorize by r, in which case this is equal to r times a prime times n plus b prime times m, which means that r divides the GCD of a and b. We now prove another very important consequence of the Bezel identity, which is the Gaussian Lemma, due to His Excellence Carl Friedrich Gauss. Our lemma says if a divides bc and GCD of a and b is equal to 1, which means that a and b do not share any common divisor greater than 1, then A must divide C. This might seem for you a trivial fact, but it needs a correct proof. Indeed, if the GCD of A and B is equal to 1, then by the Bezel Theorem one can find two integers n and m such that 1 is equal to a times n plus b times m. Now if you multiply both sides by c, one gets that c times 1, which means c, is equal to a times n times c plus b times m times c, which we can rewrite as a and c plus b c m. But we know that a divides bc, which means that bc is equal to a times a certain integer k, and now if we replace bc by a times k, one gets that this is equal to a and c plus akm, which can be factorized by a. This is equal to a times nc plus km, which is a multiple of a. Hence, A divides C. Now we apply the Bézout identity and the Gaussian lemma to the study of integral points on lines. We've seen in the previous lecture that on the line of equation 3x plus 10y equals 1, there are integral points such as minus 3 and 1 here, and the point 7 minus 2. We've also seen that the formula 10k minus 3 minus 3k plus 1, where k is an integer, gives infinitely many integral points on this line. And this is mainly because if you plug these coordinates into the equation of our line, you find that 3 times 10k minus 3 plus 10 times minus 3k plus 1 is equal to 1. This formula gives infinitely many integral points on our line L. But the good question is, are all integral points on our line L are of this form? The answer is yes, and is a consequence of the Gaussian lemma. Indeed, let xy be an integral point on our line L, which means that we have 3x plus 10y equals to 1, and we would like to show that x and y are of this form here. Now we know that the point of coordinates minus 3 and 1 is an integral point on our line L, which means that 3 times minus 3 plus 10 times 1 is equal to 1 as well. Now if you subtract the second equation to the first, one gets that 3 times x plus 3 plus 10 times y minus 1 is equal to 1 minus 1, which is equal to 0. This is equivalent to the fact that 3x plus 3 is equal to 10 times 1 minus y. Let me remind you that all the numbers here are integers, and this means that 3 divides the number 10 times 1 minus y. But the GCD of 3 and 10 is equal to 1, which means that 3 does not divide 10 actually, and by the Gaussian lemma, one can deduce that 3 must divide 1 minus y. Therefore, there exists an integer k such that 1 minus y is equal to 3k, or more equivalently, that y is equal to minus 3k plus 1. So y is of this form here. Now why is x is of this form? Actually, from our equation here, one deduces that 3 times x plus 3 is equal to 10 times 3k, and if you simplify both sides by 3, one gets that x plus 3 is equal to 10k, which is equivalent to x equals to 10k minus 3. Bingo! We now move on to a second example, and let me remind you that we've also seen that the line L' of equation 3x plus 12y equals 1 contains infinitely many rational points but does not hit any integral point. So when does the line of equation ax plus by equals c contain an integral point? The Bézout identity answers this question and actually a little bit more. We will see that if a line contains one integral point, then it contains infinitely many integral points. Indeed, a line L of equation ax plus by equals c contains an integral point if and only if the GCD of AB divides the number c. The first sense is actually obvious because if x0, y0 is an integral point on our line L, then we must have ax0 plus by0 equals to c, and this obviously means that the GCD of AB divides c because the GCD of A and B must divide every linear combination of A and B, namely c in our case. Let us now prove the converse. We would like to prove that if the GCD of A and B divides C, then the line L must contain an integral point. Indeed, by the Bézout identity, we know that we can find two integers n and m such that the GCD of AB is equal to a times n plus b times m. Now if the GCD of AB divides C, this means that we can write C as the GCD of AB times a certain integer k. But now if we replace the GCD of AB by the linear combination of A and B here, one gets that this is equal to AN plus BM all times k, which is equal to A and k plus B mk. Hence the point of coordinates nk and mk is an integral point on our line, and this ends our proof. Let us see how this concretely works and consider the line L of equation 25x plus 13y is equal to 3. We see here that the GCD of 25 and 13 is equal to 1, which divides obviously the number 3 corresponding to our C. This means by the previous theorem that our line L here must contain an integral point. And let us compute it using the extended Euclidean algorithm. We first start by dividing 25 by 13. We get that 25 is 13 times 1 plus 12. Then we divide 13 by 12 to get that 13 is equal to 12 times 1 plus 1. And finally, we divide 12 by 1 to get that 12 is equal to 1 times 12 plus 0. We see here that our GCD is 1, and if we work the algorithm backwards, we get that 1 is equal to 13 minus 12 times 1, which is equal to 13 minus 25 minus 13 times 1, all times 1, and this is because actually 12 is equal to 25 minus 13 times 1. I got this from here, and after simplifications, this gives 13 times 2 plus 25 times minus 1. So I wrote here the GCD of 25 and 13, which is equal to 1, as a linear combination of 13 and 25. Now multiplying both sides by 3, one gets that 3 times 1 is equal to 13 times 6 plus 25 times minus 3. This actually means that the point of coordinates minus 3 and 6 is our integral point on the line 25x plus 13y equals to 3. Very nice. Now, as I said before, if a line contains one integral point, then it must contain infinitely many of them. So I suggest we go chase all the other integral points. Indeed, if xy is an integral point on our line, then we must have 25x plus 13y is equal to 3. But now we know that the point minus 3, 6 is on our line too, which means that 25 multiplied by minus 3 plus 13 times 6 is equal to 3 as well. Subtraction the second equation to the first, one gets that 25 times x plus 3 plus 13 times y minus 6 is equal to 3 minus 3, which is equal to 0. This is equivalent to the equation 25 times x plus 3 is equal to 13 times 6 minus y. Now let me remind you that all the terms here are integers, and this means that 25 divides 13 times 6 minus y, which means that 25 must divide 6 minus y, and this is by the Gaussian Lemma because of 25 of 13 share no common divisor, greater than 1 of course. Thus, there is an integer k such that 6 minus y is equal to 25 times k, which is equivalent to the equation y is equal minus 25k plus 6. This means that all the y's are of the form minus 25k plus 6, and if you plug this here, one gets that 25 times x plus 3 is equal to 13 times 25k, and by simplifying both sides by 25, we get that x is equal to 13k minus 3. This means that all the integral points xy are of the form 13k minus 3 and minus 25k plus 6. Now does this really work? Actually it does, because if you do 25 times 13k minus 3 plus 13 times minus 25k plus 6, and I'll leave it to you to see that this is equal to 3 for every integer k. Our exciting lecture ends here, and we will get involved with more number theory in future lectures. Thank you for listening.